to Two Projects. In this video, we are going to explain the project Short-Term Arrival Delay Time Prediction in Freight Rail Operations using Data-Driven Models. Introduction. The primary aim of this project is to develop a data-driven model for short-term arrival delay time prediction in freight rail operations. This model focuses on accurately estimating the time it takes for goods transported by rail to arrive at their destination station by station. Freight rail is a vital mode of transportation for daily goods, and accurate arrival time prediction is crucial for efficient logistics and supply chain management. Traditional methods for arrival time prediction are limited by their reliance on simplistic distance and travel time calculations. These methods do not consider short-term variations that can affect arrival times, leading to inaccuracies and potential delays in the transportation process. As a result, there is a need for more sophisticated and data-driven approaches. This project addresses the need for more accurate predictions, which can have a significant impact on the reliability and efficiency of freight rail operations. And in this project, we introduce data-driven models and machine learning algorithms to accurately predict short-term arrival delays in freight rail operations. And this project's outcomes will benefit a range of stakeholders in the freight rail industry, including transportation operators, logistics companies, and manufacturers. The accurate prediction of arrival times will enable better planning and resource allocation, reducing costs and ensuring more reliable delivery schedules. Objective of the project. So, as I mentioned earlier, the project aims to build a data-driven model that accurately forecasts short-term arrival delays in freight rail operations. This model focuses on delivering precise predictions at each station along the rail route, thereby optimizing resource allocation and logistics planning. The project involves a comprehensive evaluation of machine learning algorithms such as LightGBM, XGBoost, Random Forest, etc. By measuring their performance using standard metrics like RMSE, MAPE, MAE, and R-square, it determines which algorithm offers the most reliable and accurate arrival delay predictions. Model interpretability is a key concern in machine learning. The project addresses this by employing the Shapley technique to gain insights into the features that significantly impact high R-square scores. This enhances transparency, allowing stakeholders to understand the rationale behind model decisions. And as an extension, the project experiments with advanced XGBoost featuring 100 estimators to further optimize feature selection and enhance R-square scores. Requirements needed to execute this project are software requirements. Software of Anaconda. Primary language used is Python. Front-end framework required is Flask. Backend used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements used are operating system of Windows, processor of i5 and above, RAM of 8GB and above, and hard disk of 25GB and above. Working modules of Flow of Work. Now we'll discuss working modules of Flow of Work. The first step is importing required packages. In this step, we will import essential libraries such as NumPy and Pandas for data manipulation and analysis, sklearn for machine learning and data pre-processing, Matplotlib and Seaborn for data visualization. The second step is exploring the dataset. So the project involves the exploration of dataset. This exploration phase includes tasks like loading the data, understanding its structure, and conducting initial data analysis to gain insights into the dataset's characteristics. The third step is visualization using Seaborn and Matplotlib. In this step, we employ Seaborn and Matplotlib to create visual charts and graphs, facilitating a better understanding of dataset characteristics. The fourth step is feature correlation analysis. So this stage focuses on analyzing the relationships between different features or variables in the dataset. Identifying correlations is crucial for feature selection and understanding which attributes impact the target variable, that is, arrival delay, the most. The next module is feature importance with LightGBM. So the project employs LightGBM, a gradient boosting framework, to determine the importance of each feature in making predictions. Feature importance helps in selecting the most relevant attributes for the model, contributing to its efficiency. The next step is data pre-processing. So data pre-processing encompasses tasks like normalization, dealing with missing values, and preparing the data for model training. It ensures that the dataset is in the best state for accurate machine learning. The next step is train and test split. So in this step, we segregate the dataset into training and testing subsets. The training subset is used for model learning, while the testing subset evaluates the model's performance on new data. The next step is train and evaluate machine learning models. So multiple machine learning models are trained using the prepared dataset. These models are evaluated using various performance metrics like RMSE, MAPE, MAE, R-square to determine their accuracy and suitability for arrival delay prediction. And in the next step, as an extension, the project explores the advanced XGBoost algorithm. It uses 100 estimators, that is trees, to enhance feature selection and ultimately improve prediction accuracy, that is R-square scores. And in the next step, Shapley, that is Shapley additive explanations, is applied to interpret the models by revealing which features have the most significant influence on achieving high R-square scores. This improves model transparency and understanding. And the next step is performance comparison. So a comparison is made between the different machine learning models used in the project. The performance of each model is assessed and the results are analyzed to determine which model is the most effective for arrival delay prediction. And the project extends beyond model development by creating a user interface using the Flask framework. This interface facilitates user interaction, authentication, and input submission for delay predictions. And the next step is Flask framework with SQLite for sign-up and sign-in. So in this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So in the next step, users provide input related to freight rail operations. This input undergoes pre-processing to prepare it for model predictions. The trained machine learning models are employed to make predictions based on user input. These predictions consider factors such as train length, wagon quantity, and other features to estimate arrival delays accurately. And the model's predictions along with arrival delay estimates are presented to users through the front end. This user-friendly interface ensures that the results are easily accessible and interpretable. Now we'll understand the algorithms used. The first algorithm built is LightGBM, that is Light Gradient Boosting Machine. So LightGBM is a gradient boosting framework that focuses on speed and efficiency. It is particularly useful for this project because of its high computational efficiency and ability to handle large datasets. With a histogram-based approach for tree building and parallel computing capabilities, LightGBM can provide fast and accurate predictions for short-term arrival delays. The second algorithm used is linear regression. So linear regression is a straightforward algorithm used for modeling the relationship between the target variable, that is arrival delay in this case, and the features. It serves as a baseline for evaluating model performance in this project. The next algorithm built is KNN, that is K nearest neighbors. So KNN is a non-parametric algorithm that makes predictions based on the similarity of data points. It can be valuable for this project when considering the local context of a station's historical data to estimate delays. Its simplicity and ability to capture local patterns make it a suitable choice. The next algorithm used is random forest. So random forest is an ensemble method that combines multiple decision trees to make predictions. It is known for its robustness and ability to handle noisy data. In this project, random forest can capture complex relationships and provide reliable predictions, which is crucial for accurate arrival time estimates. And the last algorithm built is extension XGBoost. So XGBoost, that is Extreme Gradient Boosting, is an advanced gradient boosting algorithm known for its high performance. The extension of XGBoost with 100 estimators aims to optimize feature selection and enhance R-square scores. This advanced algorithm can potentially offer superior predictive accuracy, which aligns with the project's goal of precise arrival delay prediction. So this is the comparison graph comparing R-square and RMSE of different algorithms. In this graph, on x-axis I have algorithm names, and on y-axis I have RMSE and R-square scores. So R-squared is a measure of how well a regression model explains the variance in the target variable, with higher values indicating a better fit. And root mean square error, that is RMSE, quantifies the average size of prediction errors, with a lower RMSE suggesting better model accuracy. So R-square assesses overall model performance while RMSE gauges prediction error magnitude. So we can see XGBoost is doing well in both R-square and RMSE when compared to all other models in this particular project. So the algorithm which is best performing will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is the dataset folder in which I have data and test data files. I'm opening the data file. So this is the dataset on which we will train the machine learning models. And this is test data which doesn't have the target variable, that is arrival delay column, which we will predict using the trained machine learning models. This is static folder which consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And this is model file which contains algorithm information. This file will be loaded into the project during runtime. This is notebook IPYNB file. This Jupyter notebook file contains combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. Now copy the path of the code folder from the address bar of the file explorer. I'm copying it and open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. So I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. So after running the app.py file, the Flask framework will host the application locally at the default address, local host and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a register link, click on it. So if you are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on the sign in link. So here we have to provide our credentials, username and password. And click on sign in button. So it has redirected us to the real-time delay prediction page. So here we have to fill in these parameters. First we'll understand these parameters. The first one is TEU, that is 20 foot equivalent unit. It measures cargo capacity with 20 foot container equivalents, impacting freight load and potential delays in rail operations. The next one is train length. So the length of a train plays a vital role in scheduling and potential delays. Longer trains may have different operational requirements and may encounter varying arrival times at stations. The next one is wagon quantity. So wagon quantity is the number of rail cars or wagons attached to a train directly affects its capacity to transport goods. The next parameter is train weight. So train weight is the mass or weight of the train, including cargo and rail cars. It is a critical factor that can impact both efficiency and operational aspects. The next parameter is distance station. So distance to a station is the distance between the train and the next station along the rail route. It is a fundamental feature for predicting arrival times. It directly influences how long it will take for the train to reach the next stop. And the next parameter is total distance. So total distance is the cumulative distance from the starting point to the destination, and it is a significant factor for arrival predictions. It accounts for the entire rail journey's length, helping estimate the time required to complete the trip. And the last parameter is departure delay. So departure delay, that is delays in the departure of the train from a station, are a direct source of arrival delays. Understanding the departure delay is crucial for accurate arrival time predictions as it reflects the time lost during operations. Now we'll fill in these parameters. TEU would be 98, train length would be 5, wagon quantity is minus 11, train weight would be 194, distance station would be 1448, total distance would be 430, and departure delay would be 408. Now click on predict button. So here we can see the result. The rail delay time is minus 18.8. That means the train reached station before arrival time. Click on home link. We'll give another set of parameters now. TEU would be 1173. Train length would be 30. Wagon quantity would be 3. Train weight would be 203. Distance station would be 1747, total distance would be 711, and departure delay would be 656. Now click on predict button. So the rail delay time is minus 10.8. Minus indicates that the train reached station before arrival time. Now we'll try giving another set of parameters. TEU would be 168. Train length would be 125, wagon quantity would be 72, train weight would be 175, distance station would be 1440, total distance would be 549, and departure delay is 632. Now click on predict button. So we can see the rail delay time is 19.7. Now click on logout. So the conclusion here is the project successfully developed data-driven models for precise short-term arrival delay prediction in freight rail operations, addressing the need for accurate arrival time estimates at various stations. The performance of multiple machine learning algorithms including light GBM, linear regression, random forest, KNN, and extension XGBoost was assessed using key metrics. Extension XGBoost demonstrated superior accuracy with the highest R-square and the lowest RMSE and MAPE values. The project enhanced model interpretability by employing Shapley to identify the features that contributed most to high R-square scores, allowing stakeholders to gain insights into the prediction process. The project applied essential data processing techniques such as normalization and handling missing values. Feature selection and correlation analysis were also performed to optimize model performance. And the accurate arrival time predictions generated by this project have significant practical implications for transportation operators, logistic companies, manufacturers, and the research community. These predictions can lead to improved resource allocation, reduced costs, and more reliable delivery schedules, ultimately enhancing the efficiency and effectiveness of freight rail operations.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, Please visit True Projects YouTube channel and subscribe.